Hi scholars! Today we'll cover the Monotone Convergence Theorem. While you may not know the name, the concepts in its statement are likely familiar. The Monotone Convergence Theorem, or MCT for short, states each monotone sequence of real numbers converges if and only if it is bounded.
Sarah, this seems pretty abstract. Why do we even need to understand this theory?
Yeah, that's a really good question. Although its statement is abstract, it enables key results in many disciplines of math, such as this course, Real Analysis, Probability, Statistics, Economics, and Optimization. Knowing and understanding the Monotone Convergence Theorem will put a very powerful tool in your belt.
Alright, I'll bite. I don't see how, but that does seem important. Still, I am confused about what it means to be monotone, since that just makes me think of a robotic voice. How does that relate to numbers?
No, that's not what we meant by monotone here. Let's define the term now. We say a sequence S sub n is monotone, provided it is either non-increasing or non-decreasing. A sequence of real numbers is non-decreasing, provided each successive iterate is always at least as big as the current iterate. That is, S sub n plus 1 is greater than or equal to S sub n for all indices n. If the inequality is strict, then we can say the sequence is strictly increasing. Similarly, a sequence S sub n is non-increasing, provided each successive iterate S sub n plus 1 is not greater than the current iterate S sub n. So, if we know a sequence is non-increasing, then it's monotone. However, note, if it's monotone, then we might not know if it's non-increasing or if it's non-decreasing.
Oh, okay. That makes sense, but why do you say non-decreasing rather than just say increasing? Wouldn't that be simpler? Or am I missing something?
Oh yeah, that's actually a pretty subtle point. We could say the sequence is increasing, but then we should also add another word to clarify that the inequality is not necessarily strict, since sometimes increasing is interpreted as saying each successive iterate is bigger than the last one, but our theorem applies even if the next iterate is the same as the current one.
Ah, I got it.
Great! And for now, you can think of bounded as keeping a sequence from blowing up to infinity. Before we get into the specifics, let's go through a basic example of the monotone convergence theorem. Imagine a ball rolling down a hill. We know that the height of the ball will keep decreasing as long as the hill is slanted. And once the ball reaches the flat ground, its height will remain unchanged. Intuitively, we know that pushing a ball to start rolling down a hill will make its height eventually match ground level. If you understand that, then congrats! You understand a main conclusion of the monotone convergence theorem. That's really the core of it. If you have a sequence going up or down, and have a sort of wall preventing it from going too far in that direction, then eventually the sequence will converge. Otherwise, it'll keep on going forever. To make it more intuitive, I'm going to use real-world examples, and then we can return back to the diagrams. There are 4 possible cases. First, we can have a sequence that's monotone and unbounded, like a rocket ship's trajectory from its launch pad as it flies out into space. Second, the sequence could be monotone and bounded, such as the height of a balloon in an enclosed mall. Third, we could have a non-monotone and bounded sequence, like the height of a bouncy ball when you drop it. And lastly, we could have a non-monotone and unbounded sequence, like a satellite that orbits around Earth with its distance from Earth oscillating but tending to get farther and farther away each time it orbits. Understanding these 4 different examples and the corresponding types of sequences will help us prove whether the sequences converge or diverge. Now let's formalize the term bounded. A sequence S sub n is bounded provided there is a positive number m such that the absolute value of S sub n is less than or equal to m for all natural numbers n. As an example, consider the sequence S sub n equals 10 plus 1 over n squared. In this case, each S sub n is bounded by 11. However, the sequence with S sub n equals n is not bounded. We can see that it's not bounded because the plot keeps going up and up. Now it's time to get to the actual proof. It has 2 parts. Since the theorem uses the phrase if and only if, we prove the sequence converges, then it's bounded. And in a separate step, we also prove bounded monotone sequences do converge. For our proof sketch, we're just going to consider sequences that are non-decreasing. An analogous argument can be used for non-increasing sequences. First, we're going to show if a sequence converges, then it's bounded. To do this, suppose we have a sequence s sub little n which converges to a limit z. This implies there's a big N such that the absolute value of s sub little n minus c is less than or equal to 1 for all n greater than or equal to big N. By the triangle inequality, we know that the absolute value of s sub little n equals the absolute value of s sub little n minus c plus c, which is also less than or equal to the absolute value of s sub little n minus c plus the absolute value of z. Now, accounting for the first big N points in the sequence, we can write the absolute value of s sub little n is less than or equal to the maximum of the absolute value of z plus 1, the absolute value of s sub 1, the absolute value of s sub 2, all the way up to the absolute value of s sub big N, for all natural numbers n. This shows that the sequence s sub little n is bounded.
Wait, how are we able to show the last inequality for being bounded? I understand we get the absolute value of s sub little n is less than or equal to 1 plus the absolute value of z for all little n greater than or equal to big N. But what's going on with the max in there?
Yeah, that's kind of a subtle point. We can break it into cases. Suppose you give me an index k. If k is less than or equal to n, then we know the absolute value of s sub k is less than or equal to the max of the absolute value of s sub 1, the absolute value of s sub 2, and so on, all the way up to the absolute value of s sub big N.
Okay, that case makes sense.
Now, if k is greater than big N, then we know the absolute value of s sub k is less than or equal to the absolute value of z plus 1.
Oh, and so you can cover both cases at the same time by taking the biggest bound for each of the two cases.
Good job, you got it. The proof is now half over. So for this part of the proof, we're again going to take a sequence called s sub little n. Let x be the smallest upper bound of the sequence, also called the supremum. That is, there's no value less than x that forms a bound for a sequence. So what we're trying to prove is that the sequence s sub little n converges to x.
Okay, so if this is just a proof of convergence, do we start by letting an epsilon greater than 0 be given?
That's right. Let's take an epsilon greater than 0 and draw a line here at x minus epsilon. What we need to show is that the absolute value of s sub little n minus x is less than or equal to epsilon when little n is big. Now let's pick an index big N so that s sub big N is at least x minus epsilon.
Okay, so this value of s sub big N must exist since the sequence is of real numbers and x is the least upper bound, making x minus epsilon not be an upper bound. And so there's a number in the sequence between x minus epsilon and x.
Yep, you got it. Now consider an index little n that is at least as big as big N. Because our sequence is monotone, we have s sub little n is greater than or equal to s sub big N. Again, using the fact that x is an upper bound, we can say that s sub little n is less than or equal to x. Putting together inequalities, we can say that x minus epsilon is less than or equal to s sub big N, which is less than or equal to s sub little n, which is less than or equal to x, which is less than x plus epsilon, where the last part holds since epsilon is positive. And if we subtract x from everything in the inequality, what happens?
We get that negative epsilon is less than or equal to s sub n minus x, which is no more than epsilon, and that's the same thing as saying the absolute value of s sub n minus x is less than or equal to epsilon.
Yeah, since we start with an arbitrary epsilon and showed s sub little n is within epsilon of x when little n is big, the sequence converges to x, and now we have successfully finished the proof. Good job, that was not an easy proof, but now it's over. So now, we're going to go through a basic outline of how we conduct a proof that applies the Monotone Convergence Theorem to show a sequence converges. First, we restate how the theorem can be applied in our setting. For example, we can state by the Monotone Convergence Theorem, it suffices to show that the sequence S sub n is monotone and bounded to prove it converges. If your proof will also include showing the sequence converges to a particular limit, then we can add something like the part in parentheses to say how we'll get to the limit s. Next, we show the sequence is both bounded and monotone. From this, we can deduce that the sequence converges. In the final step, we can use properties of limits to derive a formula for s.
I'm not sure I get what you mean by that last step.
Oh yeah, don't worry about that. That's a super high-level outline. We'll make it more concrete in our upcoming examples. For now, you can just think of a step 3 as using algebra with limits, like you do in calculus, to rearrange and solve for the value you want.
Okay, I think I am tracking now, though I definitely do need to see some examples.
Sure thing. We'll turn to examples now. So for our first example, consider a number c in the open interval from 0 to 1. We need to show if s sub n equals c raised to the nth power, then s sub n converges to 0. Okay, our first step is to state how we plan to tackle the problem. This will ensure the reader knows what to expect and can follow all your steps. For our proof, we can essentially copy the outline of the previous slide. Notice I added explicit numbers for steps 1, 2, and 3, so the reader of our proof can clearly see what's going to come next. In step 1, we see the sequence s sub n is strictly decreasing, because if I subtract s sub n from s sub n plus 1, I see that this is equal to c to the nth power plus c minus 1, which is less than 0. Rearranging each side of an inequality gives us the inequality we want, which is that s sub n plus 1 is no more than s sub n. So for the second step of this proof, we use induction. For the base case, we know that s sub 1 equals c. If the absolute value of s sub k is less than or equal to c for some index k, then we can factor out a c from the formula for s sub k plus 1 to get c times the formula for s sub k. And then we can apply our inductive hypothesis with the fact that c is less than or equal to 1 to deduce s sub k plus 1 is bounded by c. This closes the induction, and so s sub n is bounded by c.
Okay, wait. The first step made sense, but why can you just pull the c outside the absolute value?
So the reason we can do that is because we know that c is a positive number.
And so then because c is positive and no more than 1, we can get that next inequality?
Yeah, that's right.
Alright, I'm tracking now.
In the final step, we show that the limit s is in fact 0. This is where we play around with the property of limits to rearrange it for what we want. In the first equation shown, we use the relationship between s sub n and s sub n plus 1, with the fact that the limit of s sub n is the same as the limit of s sub n plus 1. This reveals c times s equals s, for which it follows that s must equal 0. This is what's shown by the second equation, and that completes the proof.
This seems a bit sneaky. So it looks like the first two equalities just use multiplication properties of limits, which we already know. And then the third one uses the fact that s sub n plus 1 equals c to the n plus 1, which is the same thing as c times c to the n. Am I seeing that right?
Yeah, you're right. And the next inequality is also a property of limits. Basically, we know that if n is big, then n plus 1 will also be big. And so, if s sub n is close to the limit, then s sub n plus 1 will be as well.
I see. This seems like a lot of work though. Why not just provide a direct proof from the definition of convergence?
Yeah, you're right. In this case, you could have made the proof directly from that definition, but we want to emphasize here the structure and the steps of this proof technique. Our next example shows a harder example where the MCT is way more valuable. So now we're going to do our next example. For this example, we consider the sequence s sub n defined recursively as shown. We want to show the sequence converges and find its limit. To do this, we again start with the same steps as before. Now we add an extra step to show s sub n is bounded from below by the square root of c. We'll see why this is helpful in a minute. For the last step, we use limit properties again to arrive at our limit s. In step 1, the base case is given. We close the induction by using the series of inequalities shown. These are each algebraic relations. Starting from the left side, we know the square of a number is non-negative, and then we expand this and rearrange it to get what we want.
Whoa. Okay, that makes sense, but how am I expected to come up with this?
Yeah, I definitely get how it may feel a little bit like magic to pull this proof out of thin air. But the secret here is to actually work backwards. Starting with step 2, we can see that we'll get the inequality we want if s sub n squared is always at least as big as c. From that, we have reason to do step 1, which is figured out by working back from what we want on the right to something we know is true on the left. Once we figure out these tricks, then we can package the proof nicely like done here.
Okay, so like when I'm trying to figure out the proof, the inequality at the bottom of step 2 motivates step 1, and to get step 1, I actually figured out by starting at the right side and then playing around to work backwards, like you said.
Exactly. With that, we can jump into step 2, where we show the sequence is non-increasing. This is done by using the recursive relationship from the prompt and applying step 1. Step 3 is pretty short. Since we have a sequence that is non-increasing, we know s sub n is never more than s sub 1. And because we also know each s sub n is positive, we can deduce each s sub n is now bounded by c. For the last step, we again use our limit tricks from before.
Is this pretty much identical to the first proof we did?
Yeah, pretty much. Here, there's a little bit extra reasoning. Since we take a square root, we can get a positive or negative root. But we know each s sub n is positive, and so we know the limit has to be the positive root.
Ah, okay. That is slick.
Yeah, it's pretty cool. We could actually use this to compute square roots by hand if we wanted. Let's check out quickly how it converges. Here we can see a plot like before of s sub n as n increases, taking c equals 5. Notice s sub n approaches the square root of 5 very fast. In fact, it's so fast, we can't even see the error on this plot after only a few steps. Looking at the table, we can see that s sub 6 is accurate to more than 10 decimal places. In fact, if we change our plot to be of the difference between s sub n and the limit of root 5, we can see the error drop faster as we take more steps in our sequence. This is a fun example since we can rigorously show the sequence s sub n converges using the MCT, and it happens to enable us to calculate square roots pretty quickly using only addition and division.
Alright, I think I'm seeing the trend here. Can I try and give this one a go?
Of course, go right ahead.
So the first thing is that I should translate this infinite series into a sequence. The way I've seen this done before is to let s sub n be the partial sum. So like s sub 1 equals 1, and s sub 2 equals 1 plus 1/4, and so on.
Yeah, that sounds great. We can go ahead and put that as the first part of our proof.
Sweet. So to be formal, I'll write let s sub n be the sequence of partial sums for the given series. That is, s sub n equals the sum from k equals 1 to n of 1 over k squared. Now I'm lost. What am I supposed to do next?
This is a good place for us to think about the template we have for applying the MCT.
Oh, right. I can copy that opening statement from the template. So, by the Monotone Convergence Theorem, it suffices to show the sequence s sub n is monotone and bounded. I guess next I'll try and verify the properties for each of these two steps. I know the sequence is increasing since I'm just adding another positive number at each step. I'll go ahead and copy the difference of two steps in the sequence like you did to get that s sub n plus 1 minus s sub n equals 1 over n plus 1 squared, which is positive for all natural numbers n.
Perfect. You're almost there.
I'm not sure how to show this sequence as bounded.
You can start by writing what you know, and then you can try to find a number bigger than s sub n that is independent of n.
Okay, so I know s sub n equals 1 plus 1 over 2 squared, plus, and so on, up to 1 over n squared. The numbers do keep getting smaller. Okay, I know I can use a trick with fractions. In the next step, I'll write that this is less than 1 plus 1 over 2 times 1 plus 1 over 3 times 2, and so on up to 1 over n times n minus 1. I think this is helpful because this can make it so that I can rewrite the sum as the difference of terms. Essentially what we get out is a telescoping sum. Writing each of these out, almost all the terms cancel so that in the end I get 2 minus 1 over n, which we know is less than 2. Okay. So I know the sequence is always going to be between 1 and 2, and so therefore it is bounded.
Awesome work! You did great.
Thanks. Do I need to figure out the limit too?
No, for this problem, it only asks to show the series converges. It turns out in this case, it's actually non-trivial to evaluate the limit. We'll leave that for another day. So to summarize, this example shows that we can use the MCT to establish convergence, even in cases where we might not know what the limit is. That's it for today. You can check out more proofs and examples in the lessons for our course at www.typel.academy.